I'm Pat Dugas. This screencast is about finding the nth roots of expressions so we can simplify and then use those radical expressions in the form of the nth root of x. So let's get some terminology down. So if we have something that looks like this, we call this the nth root of x. Now previously we've seen no number there in what's called the index. That is assumed to be a 2 if there's no number there. It's assumed to be a square root. But now we're talking about the nth root, so it could be any root. And so an nth root is the inverse of raising a number to the nth power. So if I have something like x to the n, the nth root of x is the inverse operation to that. So some other terminology here, the radical sign itself is the symbol of this nth root operation. The actual degree of the root here is called the index. Whatever number appears there, that is the root. Now, if it is not there, then we assume it is the second or square root, which is the most common one. The radicand is the base number that's being evaluated here, radicand. And the principal root, what happens is if we're evaluating an even degree root, we could actually have positive or negative, two different answers. In those cases, the principal root is the positive or non-negative in the case of 0, the non-negative root. So let's look at an example here. This is what's called the third r cubed root of 64. So the index is 3, the third degree. The radicand is 64. We are taking the third root of 64, which is 4, because 4 to the third power gives us 64. So let's just give a mathematical definition for an nth root. For any real numbers a and b, and any positive integer n, so we're only talking about positive powers and positive roots, if a to the nth power is equal to b, then a is an nth root of b. So for example, because negative 3 to the raised to the fourth power is 81, negative 3 is a fourth root of 81. And 3 is a principal root. So the way that would actually be written, we'd have a 4, the fourth root of 81. There are actually two fourth roots of 81. It is positive 3, which is the principal root, and negative 3. Let's look at some examples of simplifying and finding the nth roots of different expressions. So let's take the square root, or second root, of 16x to the 8th. Now, in all of these nth root kind of situations, you want to look at what the index is, and there's a 2 here. It's just not shown. Looking for perfect squares of all the different terms. So I'm looking for something that multiplies by itself to give 16, and something that multiplies by itself to give x to the 8th. So I can break that up. So 16 is the same thing as 4 to the second power, and x to the 8th is the same as x to the 4th raised to the second power. So what's going to happen is, to be able to simplify this, I need to get things that are raised to the second power so that the root, the second root or square root, and second power cancel each other out. They're inverse operations. So take each term in the expression and try and find that the number which raised to that power that the index is at gets us that number. When I take the square root of 4 to the second power, I get 4. When I take the square root of x to the fourth power raised to the second power, also known as x to the 8th, I get x to the 4th. And so there are two possible roots to this, plus or minus 4x to the 4th. Now the principal root, however, is positive 4x to the 4th. But there are technically two roots that could multiply together to give me 16x to the 8th. So let's look at this example. We have negative square root of q to the third plus 5, all raised to the fourth power. So since we're talking about a 2 here, because if nothing's there, it's a 2, I'm looking at how do I get q to the third plus 5 all to a second power. Well, it's already raised to the fourth power, so if I take q to the third plus 5 raised to the second power and square it, now I have that inverse operation. So this radical, or root 2, is going to inverse out this other second degree term. When that happens, what I'm left with is this part right here, because again, the radical 2 and the 2 to the second power are inverse operations, and that's our answer. Since it's already a negative, there's only one answer or one root to this. Let's look at a couple more examples. This is the 6th root of t to the 6th. That's how we would say that. Now, since 6 is an even power, there are actually 2 roots, plus or minus t to the 6th. So since t could be negative, what we're going to have to do is call this the absolute value of t. You could also write plus or minus t, because there are technically 2 roots. Now, the positive t is the principal root, though. Let's look at another example. The 4th root of 16p to the 8th q to the 12th. So again, now I'm looking for breaking these up into power of 4 terms. So 16 is the same thing as 2 to the 4th. P to the 8th is the same as p to the 2nd to the 4th. And q to the 12th is the same as q to the 3rd to the 4th. Okay, I know that sounds like alphabet soup, but 16 is 2 to the 4th. I want a whole bunch of 4th power terms in here so I can inverse operation them out. P to the 8th is the same as p to the 2nd to the 4th. Q to the 12th, the same as q to the 3rd to the 4th. So now what's going to happen, by taking the 4th root of all these 4th power terms, what I'm left with is 2 times p squared times q to the 3rd. Of course, the examples get more complicated. Isn't that the way math seems to always work? So now I'm taking the 5th root of 243 times x plus 2, the quantity, raised to the 15th power. Again, I'm looking for things that are to the 5th power to be able to use that inverse operation in simplifying this. So 243, interesting number, can be written as 3 to the 5th power. X plus 2 to the 15th, rewritten as x plus 2 to the 3rd, all raised to the 5th power. So let's do that. Got 243, same as 3 to the 5th. Got x plus 2 to the 15th, rewritten in terms of the 5th power, it's x plus 2 to the 3rd, all raised to the 5th power. So when I take the 5th root, there go powers of 5. Now, since this is an odd index, we do not need absolute value. There is only one root, and in this case, it's the positive number. So the result is 3 to the x plus 2 quantity, all raised to the 3rd. So we looked at nth roots and the ability to simplify and use radicals in the form of the nth root of x.